Okay, let's take a look what that one actually means on MATLAB. So, just a moment, get my cursor is there. So basically, we try to do some filter on MATLAB just by defining the corner point and try to match some attenuation. I just pick some arbitrary numbers to start with. So we'll fix, for example, our sampling rate to hey, 4,000 hertz sounds good, just for fun. No, well, 8,000 sounds even better. No, we have a sound sample already, 11,025. Okay, 11,025. Sorry about that. So sampling rate, 11,025 samples per second. And then we could actually take a look at the signal that I had before. What did it look like? Let me open that one. Open. So we have a sampling rate of 11,025, and then we have 1 second long sample, 440 hertz. Added some. Okay, there. Then I added some noise on it. There, did some spectrum out of it, and let's see, somewhere I added another tone there. Okay, there it is. So I added a third harmonic just for fun. Let's see. Could we try to fix a filter so that I can get rid of that third harmonic? Maybe. Let's take a look at power spectrum. All right, wait a minute. So we have SSNN spectrogram of SSNN evaluate selection. So I got this picture. Okay. So we have about, let's see, that 1500 hertz signal starting here. I want to reduce the amount of that one with some decibels. And actually, let me start or continue here and do the just that ordinary spectrum. Okay, sub FSS and then FFT power and plot tip. Oh, okay, now I'm missing something. Missing those. Okay. Oops, PXX is not. Of course it's not. Then we have this one here, NN. Okay, decibels and maybe now I can actually. Okay, I think now I have everything here. Yes. So that's my spectrum, and for some reason I think that this 440 hertz is so beautiful sound that I want to have that one as information, and then I should reduce the this other peak here, basically say 40 dB, which means that it would go down to the current noise level. That's enough. Where the amount of attenuation actually comes from. You need to decide what is enough. One place to decide what is enough of attenuation is the noise floor. Noise floor on the pass band, basically you do not need to reduce this extra stuff or the unwanted stuff lower than that. I don't see any reason since you still have some sort of amount of noise. You should define the cutoff frequency. Closer we get it here, then we have a danger of starting to also filter some of that. So say 500 hertz maybe corner frequencies, okay. Usually a good number is 20% margin. You need about 20% margin on the for the information and the cutoff frequency. So yeah, say 600 hertz. This is not science, it's engineering. So our cutoff frequency, okay, there, 300 hertz. Not 600 hertz, just for fun. And then basically we can also, afterwards, we can tweak these. Window shape defines the stop band attenuation, and here I would say I need to have at this frequency, which is about 1300 hertz, I should have about 40 dB, maybe 50 dB attenuation on that point. 50 dB at 1300 hertz. So now I have two parameters set. This is 600 hertz cutoff frequency, and that's minus 3 dB point in our case. And then window shape is this one. Transition bandwidth actually would be the one which defines that part. So we'll first fit the window width so that we get that window shape that we get that 50 dB, and then we fit the window so that we get the stop and start frequency at 1300 hertz. Okay, so in this order, first fit the 600 hertz, then this window shape, and then do the wider window to match the transition bandwidth. On this one, you need to have something as the initial value for this window width. For example, window width of say 21. It can be anything else. It's any odd number we do, but 21, that's a good number to start. It means that in order to realize that filter, you would need actually 11 multiplications and 20 additions. Why 11 multiplications? Why only 11? Why not 21? Because this is symmetric. The window shape is symmetric, so you have the same number as a multiplier on both sides. Okay. So let's start playing with this stuff. I will close that. Get some more room. Maybe I don't need the command window either. Where did it actually go? It goes somewhere, but I don't. Woo. windowing. FIR design by windowing. So first region of interest is now symmetric on both sides. So that's actually from -10 to +10, the indexes. Is the n good number? Okay, yeah. Okay, I can actually just do it like this. My impulse response box with box window. It's simply, wait a minute. Let me do something here. Cut-off frequency is that 600 Hertz, not 6,600. Nyquist rate is Fs/2. Nyquist frequency. So half of the sampling rate. And then I can actually do the, this is the simple box. So part 1, setting up the cutoff frequency to 600 Hertz was done by selecting the sync accordingly. And my window is now the box window, and this multiplier Fc divided by Fn is the scaling term, and then we have sync of -10 to 10 indexes. So n times Fc divided by Fn. There. And it looks like this. Maybe I should also put the -10 to 10. So that's how this impulse response looks like. And basically what you would do with this impulse response, you can use it as the terms BB on filter. So you could convolute this one with the data. Okay, stem, and it's that one and zeros on both sides. And what we can do now is do the frequency analysis of it, amplitude response, just to see if my cutoff frequency is on the right place. So this is H box is actually the feed-forward parameters for the filter. The feedback term is just 1, A0. Then, for example, 1,024 points, and then fourth one is the sampling rate. So frequency response of that looks like this. So yes, I think this is quite correct, since my 3 dB point, I would guess it's somewhere in the right region. But this one doesn't have that 50 dB attenuation. It's not even close to that. So I need to get some more attenuation by selecting the window shape. It also makes this one looking much better. So I need 50 dB at 1300 Hertz. 50 dB would be in my notes. Okay. 50 dB FIR filter design. Where was it? Down that one, convolution. Okay. All right. All right. So we need about 50 dB. So Hamming, Hanning, or Blackman. Bartlett window does not quite give you that one. But for example, Hamming window does it. Okay. Those windows actually, okay, if you know one of the windows, then you can basically see the help for the other ones. That's, you go with the dock and ham. That's the Hamming window, and this is how you use it. Oh, where did it go? Ah, oh great. There we go. Huh? No. Hamming window. Hamming window. Okay. Windows. Yes, sorry, it wasn't just ham, it's hamming. And one single parameter, which is the length. However, this is a bit funny functions is it actually returns a column vector. For historic reasons, these are column vector. We need multiplication with the row vector. Okay, since this the system coefficients are defined as row vectors. And yeah, I will just show you how to do it. So what we need to do is H8 hamming. Well, H ham. Hamming window, it has the boxed thing, but then it also have hamming with the length of H8 box, and we transpose it. Transpose basically is just the one single prime there on that command. So this one is a transpose as a vector, and this now we have the Hamming window shape there, and we can do the frequency response again, not boxed anymore, but ham. See, much better. Okay, we have about 50 dB transition bandwidth, but it starts in here. It starts at 1500 hertz, and our the requirement is that it starts at least, well, at 1300 hertz. You should already have that 50 dB of attenuation, which means we need to shrink the transition bandwidth. Our current transition bandwidth is okay, that's 1500 hertz, and okay, that's 600 hertz. I will calculate that one. So 1500 minus 600. Oops. This is the current transition bandwidth. It's 900 hertz. We need to shrink that one at least down to, well, that 1300. So let's see how to do it. We need, so that was 900, and then we need to shrink it down to 1300 or 1200. Okay, we need to go from 900 to 700. meaning that we need to take 900 divided by 700 times the length of HA box elements. So we need at least 27-point filter. So we need to widen this window. So we shrink the frequency. So, but that's not a problem. So we need at least 27 filter coefficients or length of 27 points. 27 points. On HH impulse response, and okay, 27 points would be HH box. We calculate this one first. That would be 27. Exactly 27 would be from index -13 to +13. But that's absolute minimum. It's better actually to have a little bit more. And I didn't actually do I probably didn't do the perfect job on finding these stop and start frequency in any place. So, well, okay, let's try that one. We can tweak it later on. So from 13 to -13 to 13, that's 27. Filter for the purpose, maybe. Okay, so 1300 hertz is somewhere around here, so it's very close to that point. And then cutoff frequency somewhere here at 600 hertz. That should do the trick. Should do. But as you see, I would actually push this one a little bit that way more, since that's right on the edge. But well, it's always, we can always filter the signal and see what it looks like to the spectrum. Did it improve the performance, or did we get rid of that noisy term? So, of course, since we have the sample, we can always check the filtered signal spectrum, what it looks like. So, okay, SSNN, we still have that one. We filter it equals filter HH ham 1, and the signal is SSNN. Yeah, so use that HH ham as filter coefficient. There. And then we can calculate the spectrum. First, do the subsample. Was it SS sub? No. What was it? What was the sub? XX sub? Sub SS, okay. Just taking that part of it, okay, and then power of, no, power, escape. FXX, okay, FFT or sub FXX, PXX is the power, dB of it is here, and then we can plot. Ha! I have that 600 hertz, 440 hertz, almost untouched. Then I have the filter kicks in right after that peak, and now we have actually filtered that's the peak which was almost as high as this one, and we got that one much lower. So it shouldn't we shouldn't actually hear it at all anymore. So let's do the sound. So that's the original SSNN, and this is the filtered. Ha! Got rid of that third harmonic by filtering. Yoo-hoo! Good. Since now we have a nice filter, let's try something fancy here now. Frequency response of this filter. How about if we now transform this one to band pass filter, get rid of the 440 hertz. This is so much fun. Sorry. So transition bandwidth of this filter is now 700 hertz. Okay. Now let's see. We are here. Our signal is at 440 hertz, and this should be already on stop band. Our width of the filter was 600, and then it has the 700, not 1700, 700 hertz transition bandwidth. Can we get the? We might actually get even this third harmonic to hear somewhat. Okay, which means that we need to transform this filter to 440 plus 700 plus 600 would be our modulating frequency. Right. So modulating frequency basically it defines the half band. Where this cutoff frequency is here. Then we have the 700 hertz transition bandwidth. Yeah, and basically your stop and start frequency should be hitting already that one to get enough of this filtering. Okay, so modulation frequency. In this case, FM equals 440 plus current transition bandwidth plus the cutoff frequency of the original one. Okay, maybe that one. Okay, 1740 hertz. Okay, and then I will just do the FHH modulated. We start with the HH ham, then we multiply it with sinusoid, but not just any sinusoid, we multiply it by cosine of 2 times pi times modulation frequency times then the same vector what we had there from minus 13 to 30, the n vector, and times 2 for scaling. Otherwise we get the half of the gain. Okay, there we go. And That should be it. That's all. So let's see first the frequency response. Ha, why? Ah, not FM. Oh, I'm missing the not FM. That's right, but this is not the okay, divided by sampling rate. Yeah, 1 over sampling rate. So now it has the 2 pi ft sampling vector t. Okay, there we go. There we go. Ha! Excellent. So that's my filter, bandpass filter, where our second harmonic is somewhere in here. It's on the pass band, and our 440 hertz is somewhere around here. Okay. Let's try to do the spectrum again. Filt SS filter. That one, not with ham but mod. There we go. And then do the spectrum again. Sub SS. FXX. PXX. DB. And plot. Huh. Actually hear a little bit of this original 440 hertz sound, but not much. Okay, maybe. Maybe. Let's sound. Yeah, so it's a little bit of the original there. But of course, we can tweak the filter, make it to the transition bandwidth narrower to get better performance. All right, so that was the bandpass modulation, and then the low pass to high pass. Okay, let's make a design so that actually we are sure that our signal would be removed more. Okay, we have a couple of parameters already. We know that with the Hamming and 27 points, we get a transition bandwidth narrow enough and then enough of attenuation. How about if we design a filter, a high pass filter, so that we are right at the edge of that 1320, and design, for example, so that we have this 1200 hertz is the cutoff frequency for high pass filter. Then we should actually get rid of that 440 hertz signal. So using high pass. So this is the cutoff, and we have a Fs over 2 here. So that's the design parameter where we start for the low pass filter. So the cutoff frequency of the low pass that will then transform. Okay, so we start with the H8. Oh, actually, yeah. H8 box. cutoff frequency here is Nyquist rate. Well, yeah, Nyquist rate minus 1200. Same thing here. Nyquist rate minus 1200 hertz. So that's the design parameters. Yeah, and you already have the correct. And then we do the windowed version there. That's the low pass filter, which looks like this. So we have a 1200 hertz there. When we do the low pass to high pass filter transformation, we basically swap the axis. So that cutoff frequency goes there. Seeing is believing, so we make the HH mod by HH ham. Multiply this one with cosine n pi, which is practically -1 to power of from index from -13 to 13. So this actually gives the every other term is -1 and every other term is +1. See, basically this is the same as on the transfer function, you reverse the z. You replace z with -z. There. And frequency response of that. There we go. So we have low pass to high pass transformation. And now let's do the filtering again. Is in field H mode. Yeah, that's good. Sub fxx power dB and plot. Okay, so the same spectrum after filtering with this high pass filter. I think now sensors on your hearing. So all different frequency ranges actually have a part of this sensor. And if you don't have anything else on this region than just this one, you might actually hear it. Although we have much more signal coming on other places. So it depends on how well this is basically We'll see. It's on different regions, so you can actually saturate your hearing by putting white noise so that you don't hear. But on the other hand, it's also spectral component, so you might be still hearing it. Well, hopefully, let's see. Yes, that 440 hertz was removed. Not removed, reduced enough. So can't hear it anymore. Okay, good. So I have low pass, I have high pass, I have band pass, band stop filter. Would be just adding low pass and high pass together. Let me think if there is a Okay. Band stop example of the same thing. So we have the low pass version somewhere. Which one was? HH. Okay. I'll start with the same box again. No. Okay. So practically, I could make this one a band stop filter. Oh, okay. This is high pass filter. Then I could add another filter, but I don't see. Well, this case is already done, I think. Unless I go back to the design that I have, basically the 440 hertz signal goes through, but not the 1300, but then above that, say around 2 kilohertz, or let's make it 3, so it will be easier for me. Okay, at 3 kilohertz, you have the band pass there. Okay, I'll go back to my original low pass filter that passes this 440 hertz and cuts this 1300 hertz. Box HH ham is then just the window shape there. So this is the low pass filter. And frequency response, not ham, but ham. Okay, so that's the low pass part. I put the another part just for fun, starting at 3000 hertz. 3000 hertz as a high pass filter. Okay. Whoa. Let's start with the box again. But now I take the high pass box, meaning Nyquist rate minus the desired the cutoff frequency. So we are basically always starting from the defining the what is the corresponding bandwidth of the low pass filter. That's it. Okay. By the way, as you can see, I have been overriding the previous values there, so I need to be careful now. And then I will take Hamming window, but I don't want to destroy that one, so I will call it HH high, since I will be also doing the modulation here. Dot times -1 dot to power of -13 to 13. Okay, so this is also, this has a window, but it also have the window shape, but it also have the modulation. Okay, so frequency response of that high looks like that. These vectors HH high and HH, what was the other one? Ham now can be combined since they are same size. So HH band stop BST equals HH ham. So the low pass part plus the high pass part. BST. BST. There. So that's the stop band. A band stop filter. Okay, I'll just do this sound part here. So just filter SSNN field. Filter this one with the BST, and then I will do just a sound. So practically this has also the high spectral noise there remaining on the spectrum. So maybe I should still do the okay, sub something, sub sample. Then Fourier transformation power dB and plot. There. So band stop filter actually removed that part. Well, reduced that part, and the original lower and higher frequency are untouched. Okay. So yeah, those were the tricks to do on windowing method. Going back to my original. So cutoff frequency is set first, which define the sink and the gain factor for sink. Or you start with a window width. Then you select window shape according to your stopband attenuation requirement, how many dB. Then you start playing with this the window width to match this transition bandwidth so that your stop band starts at the correct frequency. And that's it. That's the whole windowing method. And yeah, so the fourth part would be do the modulation if required. Okay, let me take a quick look at the exercise. Where's FIR filters. That I have covered all of the parts of this exercise. Final impulse response systems. Okay, there's a comparison of amplitude responses of different window shapes using window width of 37. Okay. Select one of the okay. Some parameters are here missing. You can actually play with different cutoff frequencies, play with the different sampling rates, or actually just put your sampling rate at 22 or 50 and use cutoff frequency as that and play around with these different designs and how wide your window need to take in order to change transition bandwidth by factor of 0.SSS. Okay, remember the frequency is basically 1 over T. So if you increase the width by a factor, then it actually cuts the frequency by the same factor or reverse factor. Yeah. Then there's a design low pass filter. Transform it to the band pass filter. Transform or design a high pass filter starting from low pass. Then there's a noisy voice sample. See this work. There's speech and some noise. What you need to do for that You need to do the spectral analysis of the signal and try to guess which part is voice and which part is noise. And basically mark those on the spectrum and spectrogram. By the way, there are those marking tools also for the, when you open a figure, you can, maybe I should show you that. Wait a minute. On figures, there are these tools. There's also a not brush select data cursor. Where was the Let me open it on different window. Undock. I'm docking it to get all the tools. Okay, on the tools we should have the no, okay, insert. You can mark lines. You can put lines in here, for example, line in here and text also, so you can make a markings to the figure. Okay, so put the markings and basically show what is the signal level, what is the noise level, and that actually gives you the idea of how much you need attenuation of noise. And define the filter requirements, what type of filter you're using, meaning low pass, high pass, band pass, band stop. What is your cutoff frequencies, stop band attenuation, transient bandwidth, those requirements. And then design a filter that matches these requirements. Verify the design from the amplitude response and then filter the signal and try to hear what the language the person is talking. It is a language. You should recognize it. You're European. You recognize a lot of different languages as soon as you get the, you hear something about it. You probably, for example, well, not necessarily. There were some of these Scandinavian languages. So Finnish is quite easy to find, but it's not Finnish. I can say that. But Swedish and Norwegian and Danish are well, is Iceland actually. Those are very close languages. But if it's close enough, then it's close enough. This is not science, but you are not getting points from recognizing the language, but from filtering the data so that in principle it would be recognizable. Okay, good. Now you can start working on the exercise, and I'll be hanging around here until 4 o'clock.